Hello, students. Welcome back. We are going to solve one more problem from statistical mechanics. So you can see this problem. They say a atom has non-degenerate ground state and doubly degenerate excited state. So you have a system which has two levels. So one level is ground state. I call the ground state is E0. This is my excited state, which is which is doubly degenerate. That means you have two levels here. Both have a energy E1. Now we want to find the specific heat of the system of this atom. But this is here is a single atom. So we are going to find the specific heat for a single atom. Now, so first of all, we need to write the partition function, and partition function Z is given by summation e power minus beta I, and if the system has a degeneracy, then you can write GIE. Now ground state is non-degenerate, and this is a doubly degenerate, and the energy difference between the two state is E. So here the gap is given, the difference, the gap is given E. Now this makes things simpler. I can say my E naught is 0. Automatically my E1s become energy E, and now I can write the partition function. First is first energy is 0, ground state is 0. So this become, and this is this is non-degenerate. So this becomes 1, and this become GI is equal to 2. Here GI is 2 for first excited state, and energy is 2, beta energy is E. So this become a Z, and now I can find the average internal energy, that is minus del upon del beta ln of Z, or you can say this is 1 upon Z del upon del beta Z, and this is equal to minus Z is 1 upon 2 e power minus beta E, and if I differentiate this one, this will give me 2 e power minus beta E, and if I differentiate power, this will give me minus E, because I'm differentiating with respect to beta. So my internal energy becomes positive 2 e power minus beta E upon 1 plus 2 eta. Okay, so now I can make it simpler. So U becomes 2e. Okay, I divide this by 1 upon e power minus beta E. So this become e power beta E plus 2. This is my average internal energy. Okay. Now I want to find the specific heat. So that will be del upon del T internal energy U. Okay. Or you can say that is equal to KB beta square del U upon del beta. Okay. So now you can write, okay, because I'm writing this way, because CB is this one, CB is, you can also write CB as a 1 minus KB T square and del U by del beta, because del beta upon del T is minus, so here minus should come, minus this square. So if you multiply by KB here, it become beta square, you have to multiply KB here. So this is the expression for CB, and now CB is minus KB beta square. If you differentiate internal energy, this expression here, E we have to take constant because you have 2E, and differentiating this one with respect to beta, so this will give me 1 upon E beta E plus 2 whole square, and because if you differentiate this one, so this will give me beta e into e power beta e. Okay, now what happens? Cv. Okay, now we have to, so Cv becomes 2, this minus minus becomes plus here when you differentiate. So 2, okay, 2 kb e and e, beta will not come, e and e, this become beta e square because I'm differentiating with respect to beta only. So e power beta e, and then you'll get e. So this become beta e square, and then you have e power beta e upon e power beta e plus 2 whole square. Okay, now here beta e is greater than 1. Okay, beta e is greater than 1 given. That means in the denominator 2 is negligible, so you have a e power 2 beta e, and this will, if I solve this one, so Cv will be 2 kb beta e square e power minus beta e, which is given as a option C. Option C is the correct answer for this question for low temperature limit where beta e becomes very high. So you can neglect 2 and this become e power minus beta e. So this is the correct answer for this question. Hope you like the solution. Thank you very much.